Okay, so this video is a continuation of the previous video in the contour integration series. It's a direct continuation, and I'll just remind you what I did last time. So if you're watching this immediately after the previous video, then I'll just go over what we did last time. So basically, I put f of z equal to g of z divided by z squared, and g of z with this function pi cotangent pi z, and I integrated f over the boundary of this square. And in this case, this was a square of side length 2n plus 1, and it crossed the real axis at these 2 points here, and I wanted to let n go to infinity. And basically I found that the poles of this function f were precisely the integers. So when I let n go to infinity, this square is going to encompass basically all the integers along the real line, including that at z equals 0. And I found in particular that all of these poles, except the pole at 0, had multiplicity 1, so that was simple, and the pole at 0 had multiplicity 3. And that came from the fact that I had a z squared term in the denominator. Now, I've already found what the residues were. I found that the residues, if I can find it here, so I found that the residue of f at z equals 0 was minus pi squared over 3, and I found that everywhere else, so at all the integers n, where n is an integer which is not equal to 0, the residues were 1 over n squared. And using the residue theorem, I showed that the integral of s sub n is equal to 2 pi I times the sum of the residues, which in this case is the residue at z equals 0 plus the sum over 1 over n squared of the residues at everywhere else. Then I let n go to infinity, so this encompasses all of the integers along the real line. And so I ended up at this stage. I ended up with the limit as n goes to infinity of this integral is precisely equal to 2 pi I times this stuff. And basically what I want to do is I want to show that this thing is equal to 0. But that's a little bit tedious and requires some work, so I'm going to do those calculations in this video. So let's get started. So I want to use the estimation lemma. So I want to look at the absolute value of my contour integral over s sub capital N of f of z dz. I know by the estimation lemma that that's less than or equal to the length of s sub n, s sub capital N, times the maximum value of the modulus of f of z as z varies along s sub capital N. Okay, so, well, what's the length of s sub capital N? Well, this square has side length 2n plus 1. Well, the perimeter of a square is just 4 times its side length, so I'm going to have 2n plus 1 here, 2n plus 1 here, 2n plus 1 here, and 2n plus 1 here. 4 times 2n plus 1 is just 8n plus 4. So the length of s sub n is just 8n plus 4. Now when n goes to infinity, that's not enough to vanish just by itself, so I need some sort of contribution from this maximum here. So what can I do? Well, I know that f of z, so if I just look for a second at the maximum value as z varies along s sub capital N of the modulus of f of z, well, by definition of f, that's just the maximum value as z varies along s sub capital N of what? Of modulus of pi cotangent pi z. Remember, cotangent was just cosine of a sine, or 1 over tan, all divided by mod z squared. Okay, let's look at the denominator first. If you've watched my previous videos in the contour integration series, which I highly recommend you do, it'll basically follow the same sort of process with the exception of the numerator. So what is mod z squared? How can I modify this? That's the same as mod z all squared. And on my square, so on my contour, the closest point to the origin is going to be one of these points. So one of these points, these are going to be the closest points to the origin, because obviously if you can imagine, if I trace out a circle, it's going to look something like that. Well, let's see if I can do this. Well, that's quite a bad circle, but you can see that the closest points to the origin are going to be the points here, 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 and here. So basically at a distance of n plus a half from the origin. So in other words, mod z is greater than or equal to n plus a half. I've got the squared term, so that's going to be n plus a half all squared. So if I take reciprocals of both sides, that tells me that 1 over mod z squared is less than or equal to 1 over n plus a half, all squared. Okay, and by the way, I can do this because mod z is never equal to 0, and neither is this either, because n is an integer, and so the only way I could get 0 is if n were equal to minus a half, and that is impossible. Okay, so what can I do now? I've dealt with 1 over mod z squared. I now need to deal with pi cotangent pi z. So let me just put a star here so I don't forget about this, or an asterisk, and let's look at the modulus of cotangent pi z. Well, that's just equal to the modulus. Well, first of all, if I look at my contour, what can I see? Well, I want to try and parameterize one of these sides first. I'm going to have to do the same with all the sides, but let's look at this side first. So let's see if I can trace over it. So I want to look at this side. So I want to look at that side there. And what's the parameterization of that line? Well, it's going to be of the form z equals n plus a half plus iy, right? It's n plus a half because I'm staying fixed at this real number. I'm not moving in the horizontal direction or along the real axis. I'm staying right here, plus I times y. So I want y to vary between these 2 points, which are basically n plus a half and minus n plus a half. So in other words, the parameterization, if I go all the way down, I need to set, so along the, maybe if I write it like this, so along that part, along the right side of the square, the parameterization, excuse me, is going to be z equals n plus a half plus iy, and y is going to vary between negative n plus a half and positive n plus a half, and in that way it's going to trace out the entirety of that line segment of the right hand side of the square, of my contour S of capital N. So what happens when I plug z equals n into cotangent pi z, and I missed out the pi because it's not really relevant to this calculation? That's just equal to the modulus of, well, let's put the modulus right in the whole thing, of cosine of pi z, and z is this, so it's going to be pi times n plus a half plus I pi y, all divided by sine of the same thing, so that's sine pi n plus a half plus I times pi y, n modulus. And I'm going to use some trig identities here. In particular, I'm going to use the fact that cosine of a plus or minus b, that's equal to cosine a cosine b minus plus sine a sine b. And if you are not familiar with the minus plus, basically if this were cosine a plus b, I'd have cosine a cosine b minus sine a sine b, and if this were cosine a minus b, I'd have cosine a cosine b plus sine a sine b. So basically you use the opposite sign, or the alternate sign, whichever sign you choose. And the analogous trig identity for sine, I can't remember what the name is, maybe addition rule or something like that. Sine of a plus or minus b is sine a cosine b plus or minus sine b cosine a. And I'm going to use both of these trig identities and apply them to the expression above. Okay, so let's do that. So that means that this whole thing is equal to the modulus of what? Well, this is going to be cosine a, so cosine pi n plus a half, times cosine b, which is I pi y, so cosine I pi y, minus plus sine of the same bunch of stuff, so pi n plus a half, times sine of I pi y, and all of that is going to be divided by this, which is sine of pi n plus a half, cosine of I pi y, that's cosine b, plus or minus the sine of I pi y, that was b, times the cosine of pi times n plus a half. So this is quite a complicated expression already, but I can immediately do some calculation to simplify this. So first of all, what do I notice? Well, n is an integer, so that's very important for these calculations. So let me just write that down. Maybe write it down a bit neater than that. N is an integer. So what does that tell me? Well, if n is an integer, then this cosine term is going to be cosine n plus a half. If n is an integer, then this term is just going to vanish. So if n was equal to 1, I'd have cosine of pi times 3 halves, or cosine 3 pi over 2. If n were equal to 2, I'd have cosine 5 pi over 2. So this term, that's always going to be equal to 0. Okay, and likewise this is exactly the same term, so that's going to be equal to 0 too. And if this is equal to 0, this whole expression in the top left is equal to 0 as well, and this whole expression in the top right, in the bottom right, is equal to 0 too. So I can immediately cancel those out, and I'll be left with what? Modulus of this minus plus sign, but modulus of plus or minus 1, or minus plus 1 is always 1, so that's just going to be sine of pi n plus a half times sine of I pi y, all divided by sine of pi n plus a half times cosine of I pi y and modulus, and I've got the same term appearing in the numerator and denominator. I can cancel out a factor of sine pi n plus a half here, and that's going to give me the modulus of sine I pi y divided by cosine I pi y. Now recall the definitions of sine and cosine, not in terms of a triangle, but in terms of this. So recall that sine of x, that's just equal to e to the ix minus e to the negative ix over 2i, and cosine x has the definition e to the ix plus e to the negative ix all over 2. And I'm going to use these results now to expand sine of I pi y and cosine I pi y. So that's going to give me, I need some space for this, so that's going to give me the modulus of sine of I pi y, which is e to the I times I pi y, which is I pi y, minus e to the minus the same thing, I pi y, and that's going to be multiplied by 1 over 2i. I've just pulled out this and written it out front because I think I'm running out of space, and that's going to be divided by cosine I pi y, which in this case is a half. Well, to preserve the order of things, let's write this first: e to the I pi y plus e to the negative I pi y times a half. Well, I've got a factor of a half appearing in the numerator and denominator, so I can get rid of those. I've got 1 over I appearing in the numerator, but modulus of 1 over I is just 1, because 1 over I, maybe I'll write this down, so 1 over I is just the same as minus sign. You can derive that by multiplying the top and the bottom of this fraction by I, and so that means I can just get rid of that, because the modulus of that is 1. So that's going to give me the modulus of e to the negative pi y, because I squared is minus 1, minus e plus pi y, and modulus, all divided by the modulus of e to the negative pi y plus e to the pi y. Now I'm going to stop simplifying here. I mean, you could probably write this in terms of hyperbolic trig functions, but I don't need to do any more, because all I'm interested in showing is that this thing is bounded. And this thing is bounded for the following reason. I've got e to the minus pi y and e to the positive pi y here, and recall that y varies. Y varies between minus n plus a half and positive n plus a half. So this whole expression here, this fraction, is definitely bounded for any value of y that I have inside this interval. And in particular, because y is a real number, e to the negative pi y, that's going to be greater than 0, is never going to be equal to 0, because the exponential function does not touch the real axis. as long as its argument is real, and likewise this is also greater than 0. So if these two terms are both greater than 0, then their sum is also greater than 0, and the only way that this can be unbounded is if the numerator grows exponentially, which it does, but y is contained in this interval, so it does not, or if this thing goes to 0 in the denominator, but it doesn't, because these two terms mean or impose the restriction that the fraction does not blow up at 1 over 0, because that can't happen, because I've got two positive numbers added together, which means I'm going to have 1 divided by some positive number at all times. So this whole thing, this thing is bounded. Now, do I need to do the same calculation for all four sides? Well, I can actually get out of jail here, because what is the parametrization of this line? It's just going to be a reflection of the line I've just done. So if I look at the parametrization, let's draw it like this. So the side I just did was the right side of the square, and that had parametrization z equals n plus a half plus iy, where y was in this interval. But if I multiply z by minus 1, I'm going to have minus z is equal to minus n plus a half minus iy. But if y still varies along this interval, then it also follows that minus y varies between exactly the same interval. And the reason why that's true, and the reason why we chose a square, is because it results in simple calculations. So y varies between the same interval, and so does minus y. And the reason that happens is because the interval is symmetric about the origin. So the question is, if I put minus z into the calculation I've just done, do I get the same answer? The answer is yes. And the reason is the following. So I was looking at the modulus of cotangent pi z, or in this case minus pi z, and by definition of cotangent, that was just cosine of negative pi z divided by sine of negative pi z. But cosine is an even function, so this is just the same as modulus of cosine pi z. So by even function I mean that cos x equals cos x equals cosine of minus x. And that's divided by minus sine of pi z, because sine is an odd function. In other words, sine of minus x is minus sine of x. And that's just going to give me modulus of cotangent pi z. And that's because modulus of minus 1 is 1, so I'm just going to get the same function. So whether I use z or minus z is immaterial. So basically I've shown that the modulus of f, the maximum value of f along both of these sides, so this side as well, the left and the right sides, the function is bounded on each of those sides. So I've actually dealt with both of those. Now I just need to deal with the value of the function on the bottom and the top. So now I just need to look at the parametrization on the bottom and the top sides. So if I draw my square again like this, or something resembling a square, what's the parametrization of z in those cases? Well, it's going to be z equals what? Well, in this case, x is going, well, the real value is going to vary because I'm going from left to right or right to left, and the imaginary part of the number is going to stay the same. So in this case, I'm basically going to have z equal to x plus I times n plus a half. Okay, because the imaginary part is fixed, I'm varying along a fixed point on the imaginary axis for the bottom and the top, and x is going to have to vary. And in this case, x, just like y, is between the points minus n plus a half and positive n plus a half. Okay, so, oh, by the way, because I don't want to do this calculation twice, I'm going to put a plus or minus here. Right, this part corresponds to plus I times n plus a half. Let's put the x here, and this part corresponds to x minus I n plus a half. And if I put the plus or minus there, which I'm going to show you in a second, doesn't matter, then I've killed two birds with one stone. Okay, so let's look at cotangent pi z in modulus. Now I'm actually this time going to consider the modulus squared, and that's going to become obvious why I'm going to do that later. So that all squared is modulus of cosine pi z, in this case, which is pi x plus or minus pi I n plus a half, all divided by the sine of the same thing. So sine of pi times z, which is pi x plus or minus pi I times n plus a half, modulus all squared. And now I'm just going to use some trig identities again, and that's going to be equal to the modulus, well, cos a plus or minus b is cos a cos b minus sine a sine b, so that's equal to cosine pi x times what? Times cosine of pi I n plus a half minus sine of the same terms, so sine pi x times sine, and this should be a minus plus, sine of pi I times n plus a half, all divided by what? So I'm going to use the other trig identity now, which is sine a plus or minus b is sine a cos b plus or minus cos a sine b. So that's sine of pi x cosine of pi I n plus a half plus or minus cosine pi I times n plus a half times sine. Is that correct? No, not quite. So I need to have cosine of pi x here. So cosine pi x times sine of pi I times n plus a half. Modulus of that all squared. Now this looks quite a nasty expression, but trust me, it does actually simplify into something a bit nicer. So I can actually do something about, let's just get back to where I was. I can actually do something about these sine pi I and cosine pi I terms, or pi I n plus a half. So using the definition of sine, note that sine of pi I times n plus 1/2, that's just equal to 1 over 2i times e to the I times that, which is e to the I pi I n plus a half, minus e to the negative of the same thing, I pi I n plus a half, divided by 2i out front, and that's equal to 1 over 2i times e to the negative pi n plus a half minus e to the positive pi times n plus a half. Okay, now I'm going to write 1 over I as minus I, just to make things a bit clearer. So that's the same as minus I times, well, minus I over 2 times, well, let's write it like this. So minus I times e to the power of minus pi n plus a half minus e to the power pi n plus a half all over 2. And this should look a bit familiar. In fact, it is basically the hyperbolic sine function. So what is this? Let's bring the minus 1 inside. So that's the same as I times e to the pi times n plus a half minus e to the negative pi times n plus a half all over 2. And that, by definition, is just the hyperbolic sine function times I. So that's just going to be I sine of pi times n plus a half. And if you are a little bit rusty on hyperbolic functions, hyperbolic trig function especially, I'll put a link in the description box below just to some relevant articles about that, or perhaps some further explanations depending on what I write. Okay, so that allows me to replace sine pi I n plus a half. What about cosine pi I n plus a half? I can do basically the same thing. So cosine of pi I times n plus a half, using the definition of cosine in terms of exponential functions, that is just 1 over 2 times e to the I pi I, which is just minus pi to the power of n plus a half, plus e to the negative of this thing, which is e to the pi n plus a half. And you can see in exactly the same way, this is just hyperbolic cosine of pi n plus a half. So this is just cosh of pi times n plus a half. So I can rewrite this whole mess here in terms of something which is perhaps a slightly nicer mess. So this is going to be equal to the modulus of cosine of pi x times, what have I got for the next term? Cos pi I n plus a half, which in this case is cosh pi n plus a half. Then I've got my minus plus sine, and then I have sine pi x, and then I have the I shine pi n plus a half, so I'm going to have an I here, and then shine n plus a half, and I need a pi as well, so there's going to be a pi here. Now let's just write this out a bit better than that. So shine pi times n plus a half, and that's all going to be divided by some other stuff which I have here, sine pi x. So sine pi x cosh pi n plus a half, plus or minus, what was the next term? Cos pi x sine pi of n plus a half, and that's just going to be plus or minus I cos pi x times shine of pi times n plus a half, and I'm going to take the modulus of that all squared. Now recall that the modulus of a plus ib all squared, where a and b are real numbers and I is the imaginary unit, that's just equal to a squared plus b squared, and likewise for modulus of a minus b all squared, that's just equal to a squared plus b squared as well, because if you can imagine plotting these points on an Argand diagram, I'm only interested in the distance of that point to 0. That's how the norm on the complex numbers is defined. And that means I can basically write the numerator, the modulus of the numerator squared, as this term squared plus this term squared, and that's what helps get me rid of the plus or minus signs. So this is just equal to, well, that's equal to, well, I'm going to have squared, so I don't need to write the modulus signs anymore. This is just going to be cosine squared pi x cosh squared pi n plus a half plus sine squared pi x shine squared pi n plus a half, and that's the numerator, and the denominator is going to be equal to sine squared pi x cosh squared pi n plus a half plus cos squared pi x shine squared pi n plus a half. Remember, I'm just squaring each of the individual terms. Okay, so I can actually simplify this a little bit. I know that cosh of x, that is greater than or equal to 1 for all real values of x. So that means I can divide the top and the bottom by cosh squared pi n plus a half. And what's that going to give me? That's going to give me the following. So if I divide the top and the bottom of this fraction by cosh squared pi n plus a half, this term is going to vanish and go to 1. So I'm going to get cos squared pi x here. Here I'm going to have sine over cosh, which is tanh, or tan, or hyperbolic tangent. So that's going to be equal to plus sine squared pi x tanh squared pi n plus a half, all divided by what? Well, this is going to be 1, so this is going to be sine squared pi x plus cos squared pi x tanh squared pi n plus a half. So you can see it's starting to take some a much simpler form now. It's going to get even simpler. Now, there are two cases I need to deal with. On my contour as it stands at the moment, so S sub capital N, the contour is of finite size. So I need to consider two cases. I first need to consider the case where N is finite, or N is less than infinity. And secondly, I need to consider the case where N goes to infinity. And I need to prove that in each of those cases, this whole function here is bounded for all values of x and n in the necessary intervals. Okay, and by the way, in this case, x belongs to the closed interval from minus n plus a half to n plus a half. So I need to show that this whole fraction here is bounded for all these values of x. Okay, well, as n goes to infinity, recall that tanh is a function which varies between minus 1 and 1, so tanh squared varies between 0 and 1. And it's 0 whenever its argument is 0, and as x goes to infinity, tanh actually just goes to 1. So, as capital N goes to infinity, tanh squared pi n plus a half, that's just going to go to 1. So, this whole thing, let me see how can I do this? So this whole term, let's see if I can do that. That whole term, as n goes to infinity, that's just going to approach what? It's going to approach cos squared pi x plus sine squared pi x times 1, all divided by sine squared pi x plus cosine squared pi x. Let me just check that that's right. That's correct. And what is this? Well, I've got cos squared plus sine squared x over sine squared x plus cosine squared x. This is 1 and this is 1, so that's 1 divided by 1, which is just 1. So this whole thing goes to 1 as n goes to infinity. So it's certainly bounded for all values of x in this case. What about when n is finite? So that takes care of the case where n goes to infinity. Well, what about in the case where n is finite? What can I do? Well, when n is finite and x varies in between this interval, then certainly the numerator is bounded, right? Because tanh squared is a bounded function. It's going to be strictly between 0 and 1. It's not going to be 0 because I'd have to have n equal to minus a half, and it's not going to be 1 because n is finite. So the numerator looks to be fine because x is bounded in this interval. What about the denominator? I'm going to have problems if the denominator goes to 0. So if the denominator is equal to 0 at any point, then this fraction is going to be unbounded, and that's not a good thing. So first of all, let's look at this in particular steps. This function, that is greater than 0. Right, it's greater than 0. It's not equal to 0 because the only way this can be equal to 0, as I just said, is if pi n plus a half is equal to 0, and that can't happen because n is a natural number. And that's why that restriction is so important. So the only way that the denominator can be equal to 0 is if both sine squared pi x is equal to 0 and cosine squared pi x are equal to 0. But that can't happen either because this is only equal to 0. So this is equal to 0 if x is equal to plus or minus a half, not plus or minus a half, plus or minus 1, or plus or minus 2, and so on. And this term is equal to 0 if x is equal to plus or minus a half, or plus or minus 3 over 2. And these values don't coincide. There's no overlapping between these two. The intersection is empty. And so that means that I can never have the denominator equal to 0. And if the denominator is never equal to 0, and the numerator is bounded, and the denominator is bounded because x is bounded inside this interval, then that tells me that this whole fraction here is bounded. So this whole thing is bounded. So what I've now shown is that my function, f, over all of the sides of this square is in fact bounded. And if it's bounded in each of those cases, then there exists some positive real number k such that the maximum value of f along the entire square is equal to k. So in other words, I can find, so there exists, that backwards e means there exists some positive real number k such that the maximum value of f of z along my square, so S sub capital N, that is equal to k. So I can find some, basically I look at what the maximum values of f over each of the four sides, and I take the maximum value, and it's going to be equal to k. So putting it all together, what does that tell me? That tells me that the limit, rather, let's just do it like this. So the modulus of my integral over S sub capital N of f of z dz, that is less than or equal to the length of S sub n, which was 8n plus 4, times the maximum value, as z varies along S sub capital N, of the modulus of pi cotangent pi z, divided by the modulus of z squared, and this was less than or equal to 8n plus 4, divided by, well, I proved that module of z squared is greater than or equal to is greater than or equal to n plus a half all squared, so this is going to be n plus a half squared times pi times k, because that was the max value of cotangent on the square. So times pi times k. And since I've got a quadratic function in n in the denominator and a linear function in n in the numerator, this whole thing goes to 0 as n goes to infinity. So the contribution of this integral, the contour integral of f over S sub capital N as n goes to infinity, is just 0. So that tells me, so therefore, how can I do this? So let's write 0. So if I just go back, to the sum that I had, so I've now proved that this thing goes to 0 as n goes to infinity. So that tells me that this whole thing here is equal to 0. So let's just write that out. That tells me that 0 is equal to 2 pi I times minus pi squared over 3 plus the sum, or 2 times the sum as n goes from 1 to infinity, of 1 over n squared. And if I divide both sides by 2i, then I can easily get rid of this term. And then if I add pi squared over 3 to both sides, I get pi squared over 3 is equal to 2 times the sum as n goes from 1 to infinity of 1 over n squared. You can see where I'm going with this. So therefore, the sum as n goes from 1 to infinity of 1 over n squared is equal to pi squared over 6. And that is a result that we've all been waiting for. That's the solution to the Basel problem expressed in the language of complex analysis. So let's just recap what we've done. We basically, in order to evaluate the value of this sum, we set f of z to be equal to pi cotangent pi z divided by z squared, and you can see by the symmetry of the problem where that z squared comes from, and we integrated that over a square. So I suppose the natural question therefore is, can we use the same technique to tackle other sums, like 1 over n to the 4? And the answer is yes. You can actually use the same trick by setting g of z equal to pi cotangent pi z and apply that to similar sums of similar nature. And you don't just have to use the cotangent function. For instance, if you want to tackle the alternating series of this, so the sum of minus 1 over n squared, then you could, instead of using cotangent, you could use cosecant and try integrating that over a similar contour like a square. I urge you to try that for yourselves. So I hope you enjoyed this video. If you like this video or you liked what you saw, please leave a like, comment, and subscribe for more content just like this. It's been a pleasure talking to you for the past hour or so if you've been watching my videos in this playlist. So thank you, and subscribe for more content just like this. Thank you.